thanks a lot. Well, thanks the organizer for counting my talk for this presentation. I would like to present the advances of my PhD project actually on this during this talk. And maybe the main question that we could initiate the talk with is could the performance of a good magnetometer be actually enhanced when we use squeeze light to probe it? And the answer is that one of the main requirements for a device to be enhanced by squeeze light is actually to have an optical readout. And such a device I'm showing here on the first slide, where we are presenting a Bell-Bloom optical magnetometer. The atoms are polarized by a circularly polarized beam, and they are free to precess around the magnetic field. And then the linearly polarized probe beam, after passing through these atoms, it would rotate the polarization. The polarization plane would be rotated by a small angle phi, and this angle phi we are detecting by a balance detector here, consisting of a half-wave plate and the PBS. What you see here is we are actually observing the Stokes parameter S2, which has a function of the atomic interaction, which is over here, and the photon interaction. What does this mean for the noise, though? The noise in the level of having eliminated any other technical noise is consists of the quantum noise, and it is of two types: the photon shot noise that can enter here, and the spin projection noise of the atoms. These two types of noise, they don't have the same dependency of the frequency. So the photon shot noise, it is wide. It has a constant value throughout all of the frequencies, and then the spin projection noise has a different form. It is after the modulation techniques, it has this characteristic roll-off, so it looks like a low-pass filter with a time constant with a time constant of T2, the decoherence time of the atom. A similar type of frequency dependence also is there in what we call the responsivity of our magnetometer, and which shows how strong our magnetometer is throughout the frequency spectrum. So if somebody would like to calibrate for the sensitivity, what we will actually need to take into account is that the sensitivity is inversely proportional to the signal-to-noise ratio. So this the noise here goes on the denominator, while the responsivity would have to go on the denominator. Therefore, while we see that the responsivity and the combined rotational noise drop simultaneously, this does not happen up to the point that photon shot noise start to become dominant. So this means that our ratio now has two parts. One part in the sensitivity that is constant, and this is where the spin projection noise is dominating. And when the photon shot noise starts to come into play, this slope starts to increase. So what would this mean for polarization squeezing? Polarization squeezing, what it would do is to lower the photon shot noise level. So this would have two main outputs. One would be that in higher frequency it would be more evident because the combination noise would also lower, but we will also have a different crossover between the photon shot noise and the spin noise, and this would happen at different frequencies. So for the sensitivity, what this would mean is that the point that the rising up of the sensitivity would also be encountered a little bit later in frequencies. And of course, we would have a clear increase in sensitivity for higher frequency, where the combination noise has also been lowered. So we see a twofold improvement: the measurement bandwidth improvement, which refers to the measurement bandwidth refers to the frequency at which the sensitivity drops by a factor of 1/square root of 2, from its value at the lower frequency. And then we will also see the sensitivity mostly at the higher part of the spectrum to be enhanced. Squeezing of light, well, normally people refer to squeezing of light as a way to reduce optical quantum noise in intensity, phase polarization, and or beam direction. There are many methods that can be exploited for this: parametric amplification using crystals, four-wave mixing using fibers or vapors, and optical self-rotation also in vapors. And there are the potentials that those methods have can reach up to 10 dB of squeezing demonstrated at wavelengths of 1 micrometer with 1.55, 5 dB at 795 nanometer, which is more interesting for optical transitions and magnetometers, and then 3 dB is for our experiment, the mentioned squeezing. The bandwidth of those squeezers can be from megahertz to gigahertz values, which is much more than the OPMs. So those methods, along with different types of magnetometer techniques, have been used in the past decade to investigate this question whether squeeze light can help in the magnetometers. And the main result I would like to point out here is the best record so far that gives a sensitivity of 2 picotesla per root hertz for a magnetometer. The work that I would like to present today is exploiting the Bell-Bloom excitation and Faraday rotation. It's based on an optical parametric oscillator with spontaneous parametric down conversion for the squeezing, and has been exploited to achieve the sensitivity of about 100 femtotesla per root hertz with atomic densities that can reach up to 10 to the 14. The setup that we are using looks like that. I would like to focus first on the squeezer part, which is this green frame. We use an extended cavity diode laser at 700.
Is it just me?
Part of this power is amplified by a taper amplifier, and then we have a frequency doubler frequency, which is generating a blue light at 397 nanometer that will be later be used for the OPO cavity, which is the heart where the squeezing generation takes place. The OPO cavity looks like that. So basically, this is where the spontaneous parametric down conversion is happening when we are pumping with this blue light PPK-DP crystal. This is causing the amplification and de-amplification of the quadratures of the field inside, which means that if vacuum is allowed to pass through this port of the cavity, then what would come out is a squeezed vacuum, which later can be combined with a strong coherent field in terms of the PBS and give us polarization squeezing. What I would like to point out here is that we have used this setup that is mainly described in this paper, both for a magnetometer in the group and for spin noise enhancement in the past. And maybe for the purpose of this talk, it's more relevant to show the spectrum of the squeezer that looks like that. When the squeezer is off, we have the quantum noise limit part, and when the squeezer is on, we have an enhancement. You see the drop of the noise level that is mainly over these frequencies. And what is nice of our system is that it is a versatile system that can move. We have a tuning of what is the best area of the squeezer with respect to what is the best area of the magnetometer. So we can find the optimum analysis frequency and tune our system in this part of the spectrum. So having said that, I can move to the description of the magnetometry of the magnetometer. The heart of the magnetometer is consists of a rubidium cell of 3 centimeters rubidium-87 with 100 torr and buffer gas. We have a heater that allows us to go to 190 degrees of temperature, which corresponds to 10 to the 14 atoms per centimeter cube. And the magnetic field, 4 new metal sheets for magnetic field shielding. The technique is Bell-Bloom excitation again, which is achieved using a PAM, a circularly polarized PAM beam that is frequency modulated around the D1 transition. And when this causes the signal of our magnetometer to look something like that. So we have the main part is an oscillatory signal that is at the modulation frequency of the pump. And when we turn off the modulation frequency of the pump, we see the FID signal that looks like this. From fitting of the FID signal, we can get two parameters, the T2 decoherence time and the A naught, which is the maximum amplitude of our magnetometer. Then for the sinusoidal part, the main part, what we get is the power spectral density and the rotational noise or polarization noise after the digital lock-in demodulation that uses the signal from the pump as a reference. Therefore, we have now the two parts of our equation for the sensitivity. We can get the responsivity using these two parameters, the A naught free parameter and T2, and we also have the noise, so we can calibrate for the sensitivity of our magnetometer. The actual data that we can have, I show you here for a bias field of 4 microtesla that corresponds to 29.8 kilohertz modulation frequency. We can get a spin projection noise spectrum that looks like that. Here you can see the two areas, the photon shot noise curve and the spin projection noise curve, that give us the spin projection noise limited area in lower frequency and photon shot noise limited area in higher frequency. Now, if we turn on the squeezer, what happens is exactly the lowering of the photon shot noise level. And you see that the crossing is happening also at different points, at the later point. And this has such an impact on the spin projection noise area and the photon shot noise as well. Now we turn on the pump of the magnetometer. So we have the blue curve that you see already our spectrum starts picking up some noise from the 50 Hertz spikes, but other than that, there is a nice coincidence. They overlap with the spin noise spectrum. And when we turn on the squeezing on top of that, we get the squeeze magnetometer that looks like that. It has dropped also by an equivalent degree the noise floor for the photon shot noise. So what does this mean for the sensitivity? The coherent magnetometer would have a curve that looks like that. Then with squeezed light probing, we will get a lowering, especially at the higher frequency. And if we would like to compare the two, we would see that the most impact would happen at the higher frequency, where it's photon shot noise dominated. At this transition region, we would also see some benefit. And for example, at 1.5 kilohertz, we get from 480 femtotesla for the coherent magnetometer to 420. And we have an enhancement of the measurement bandwidth by about 50 hertz that is mostly seen in this transition region. So to conclude, I've tried to describe the impact of light squeezing on a high-performance magnetometer that is twofold in terms of the magnetometer sensitivity and the measurement bandwidth. The technique that we are using is polarization squeezing of light and on a Bell-Bloom optical magnetometer. And this has two, we have already seen a lowering of the magnetic noise floor that has an impact on the sensitivity at higher frequencies. We also have seen in the transition region, now we have a better access to areas of the spectrum that was obscured before from the roll-off of the responsivity AF. And even more interestingly, this experiment is a very nice platform for understanding better the interaction between photon shot noise and spin projection noise in the future. So with that, I would like to thank all of Morgan Mitchell's group in Barcelona for their contribution to that, and especially the hot atoms people that are highlighted with red here, Ricardo Jimenez, Jack Kong, and Gianvito Lucifero for helping a lot in this project. Also Dominic Hunter for being helpful with FID discussion, FID fitting discussion, and Michael Taylor and Sven Bondersen for being very helpful in the lab as well. And I would like to thank you for your attention, and I'm happy to answer any questions.
So thank you for the talk. So I think you hear several people clapping already, at least in your heart. So the session is open for questions. You can, I think it is possible that you unmute yourself. And you also can use the chat, and I think, Hara, maybe you could read something in the chat if there's something coming up. Oh yes, there is Kaspar Jensen coming in the chat. Hara, it's your turn.
I cannot, I'm not very sure.
So I read the question for you. First of all, Kaspar, thanks for the nice talk. Very good. It seems like the improvements in sensitivity and bandwidth are around 10%, even with quite a lot of squeezing 3 dB. How can you get bigger improvements?
So this is actually the 3 dB. I wanted to thank you for your question, first of all, and I would like to clarify that the 3 dB is actually one of our previous records. What I've been mentioning here, the squeezing is a little bit lower, so something like 2.6 maybe before the atoms, and 2.3 maybe after the atoms. This difference on squeezing is happening due to the losses from absorption or loss in the optical components in the way through the magnetometer, basically. So one way to achieve something better is tune our atomic density, basically, so that to have less absorption of the probe beam and increase and therefore less squeezing lost through the atom-light interaction. And one way that I can think of is would be this, yes.
Okay, there's another question coming in. Hara, do you see the chat, or should I read it for you?
Unfortunately, no.
I think in your control bar, there's a chat option.
Ah, okay.
How do you know you are spin noise limited at low frequencies? Did you experimentally verify it? For example, by varying the atom number? Did you try other squeezing modes, intensity, for example? What is your background field and the background noise level? And thank you for the nice talk. So Arne Wickenbrock was also very kind.
Thanks a lot. Okay, so if the one indication that would show that we are very close to be spin noise limited in the magnetometer. We are actually not, I want to say. So in the lower frequency part, if we check on this part of the spectrum, what we see is that in the lower frequencies we have almost a nice overlap between the magnetometer spectrum and the spin noise spectrum. But the magnetometer spectrum and the spin noise of the two, of the polarization ensemble and the non-polarized ensemble, is not the same. It's actually the case that the polarized ensemble has a little bit lower spin noise. So if we would like to be spin noise limited, we would probably have to have the magnetometer spectrum a little bit lower than the spin noise spectrum at the lower frequencies. So the answer is that unfortunately we are not spin noise limited. What I was showing in this area is what the spin noise area, spin projection noise limited area would look like for the spin noise spectrum, and I mean on this part. I haven't tried to use other types of squeezing. Unfortunately, we have this OPO squeezer in the lab available, so that was the first thing to test the squeezing with, and the background field and my background noise level. Meaning in terms of technical noise in this part?
No, I just meant at what frequency is your system? What's your alarm frequency?
Yes, 29.8 kilohertz, and this is because the bias field is at 4 microtesla. So this gives us this frequency has been chosen so that it is in agreement with that plot that I was showing you before. And it is the frequency that the magnetometer and the squeezer has both a very nice performance. Okay.